So we moved from linear programming to network flows, and we argued that network flows should also be a useful problem for modeling other things. So let's look at an example like that. So suppose we have a situation where there are 5 teachers and 5 subjects, and some teachers are capable of teaching some of these subjects. So our goal is to now find, of course, an allocation of teachers to subjects. So each instructor is willing to teach a set of courses. Some of them are willing to teach more than one course. So for instance, Deb here is willing to teach both English and history, and Priya is willing to teach both biology and maths. On the other hand, some subjects have more than one taker. So maths is also offered or can be offered by Kumar, right? And similarly, history can also be offered by Sheila. So we now have to do this allocation, right? We have to allocate courses to instructors. So what do we want to do? We want to find an allocation so that each course is taught by one instructor. There's only one instructor per course. But we also want to keep the instructors happy. So every instructor should get a course which he or she is willing to teach. So we should not be just say, we could always do an allocation this way, right? Just go across and say the first instructor gets the first course, the second instructor gets the second course, and so on. But we want to respect these edges. So we want to make sure that the allocation respects these edges, right? So this is an example of what is called bipartite matching. So in bipartite matching, we have a graph. So we have this graph, but the graph has some extra structure. So there are 2 sets of vertices. So we have a set here which I will call V0, and a set here which I will call V1, right? And all the edges actually go across these 2 partitions. So there are no edges from V0 to V0, and there are no edges from V1 to V1. So there is no edge from a teacher to another teacher, and there is no edge from a course to another course. All the edges go from teachers to courses. And now we want to find a subset of edges such that no 2 share an endpoint. So if I choose this edge, for instance, right, then I am not allowed to choose this edge, because that would correspond to offering Priya offering 2 courses, which is not allowed. So if I choose one edge which Priya is incident on, the other edge must go. Similarly, if I choose, for instance, this edge and allocate history to Dev, then I should not choose this edge, because if history is already part of an edge, history as a subject has been allotted a teacher, I should not try to allot a second teacher. So that means formally that this node should not have 2 edges in the matching incident on it, right? So we want to take a subset of edges so that no 2 of them share an endpoint. So this is called a matching for obvious reasons, because you are matching up a vertex in one set with a vertex in the other set, such that these matching vertices are connected by edges, and the matching is guaranteed to be kind of 1:1. That is, no vertex is matched to more than one vertex on the other side, right? So here, for instance, you could construct a matching. So Aziz can only teach physics, Priya can only teach biology, right? And now you have to make a choice. So Sheila can only teach history, so you should allocate history to Sheila. And now once you have allocated history to Sheila, right, then you should give English to Dev, right? And finally, once you have done this, Priya has already got biology, so Kumar should get maths. Right? So this becomes now a largest matching, in which actually every teacher has got a course and every course has got a teacher. So if you have an equal number of things on the left hand side, if so here the size of V0 is 5 and the size of V1 is 5, then you can hope to do this, right, to match everything on the left by everything on the right. So this kind of a matching is kind of, it is not only the largest, but it is one which actually matches everybody. So this is called a perfect matching. So one of the problems which arises very often is this kind of perfect matching. So here is a question of allocating courses to teachers. You can also think of any other resource allocation. So supposing you have a pool of vehicles and you want to allocate drivers to drive these vehicles, then the same problem, right? You need to allocate a driver to a vehicle that he or she is comfortable driving, and you need to make sure that all the drivers are driving only one vehicle, and each vehicle is being driven by somebody. So in many of these resource allocation kind of questions, you can have a matching. You can also think of matching in different contexts, like for instance, if you have a bunch of students on the left hand side and a bunch of institutions on the right hand side, right? So there it's not anymore 1:1, because more than one student can be matched to an institution. But you can imagine that if it's a bunch of preferences, right? So supposing I have given a bunch of preferences for which courses I want to take, then I can only get matched to one of them. So matching in different forms is a very important problem, but this bipartite matching is a particularly simple and appealing version of the problem. So we said that we are going to use flows, so let us see how we would use flows. So what we want to do is to convert this to a flow problem. So remember, in the flow problem, we have a source node and a sink node. right? So here is a source node and here is a sink node. So I have created a new source node and a new sink node, and now I want to think about this matching as a flow. So I want to think about the fact that if Sheila is going to teach history, then I am going to flow something from English to history, from Sheila to history, right? So now the flow will represent what all can go from the left to the right, and now because the flow is such that the capacity is going to be set to 1, I cannot flow 2 units of things, so I cannot flow more than 1 unit through any of these edges. So if I now have 5 edges coming out from here to the 5 instructors, the question is, can I actually flow 5 units? If I flow 5 units, then each of them must go out, right? So there must be 1 unit of flow on each of these edges. There is no storage, remember, so that if it goes out, it must go out of that node. So all this flow must leave these respective nodes in some direction, right? And once it leaves in some direction, they will reach the other side. But now, because of the capacity constraint, supposing I allocate in this flow, supposing I actually allocate both Deb and Sheila to history, then I cannot push that flow out on the other side without storage, because if 2 people are assigned history, then it's going to create a problem, because only one of those flows can go to the target, and then I have to store that flow. So you can easily see now that checking if we have a bipartite matching corresponds to finding a maximum flow in this. If I get any maximum flow, I can translate it into a bipartite matching, and every bipartite matching will actually correspond to a flow. So if I want to find the maximum or the largest bipartite matching, it corresponds to finding the maximum flow. So we want to find a maximum flow from S to T under these constraints, where I have added a source which connects to everything in V0, I have added a target which connects to everything in V1, and then I put a capacity 1 constraint on all the edges in the network. So this is an example, this and other things that we have seen are examples of what we call reductions. So we want to solve a problem A. So in our particular case, this could be bipartite matching, right? So we want to solve A. What we know how to solve is something else. So this is bipartite matching and this is network flow, right? So we know how to solve network flow because we have the Ford-Fulkerson algorithm. What we now do is convert our problem from bipartite matching to network flow. So this is where we add S and T and we have capacity 1 and so on. So we convert our bipartite matching problem to a network flow problem. And once we have a network flow problem, we have a solution for that network flow problem. So the network flow problem will tell us, the solution will tell us which all edges have flow. And in this case, the edges which have flow correspond to the edges which we allocated in the matching. So we can now reverse this thing and reconstruct from the answer that the algorithm B gives us, we can reconstruct an answer for A. So we get an answer for the original problem. So this is what we wanted, right? Given A, we wanted the answer that A should provide for X. So what we do is we pass that answer, the question to B, look at the answer of B and then reconstruct. So this is a reduction. So we say that A reduces to B, right? If I can solve B, I can solve A. So solving A reduces to solving B. So if we do this, as we have seen, if you could do this fast, right? And of course, if you can do the translation fast, so that's also there, right? Then you can transfer an efficient solution for B to an efficient solution for A. Right? Provided it does not take you too long to do these 2 steps, and you know that this step is going to be quick, then combined the whole thing is going to be quick. I have to do some work, call this B, get the answer from B which will be quick, and then reconstruct the answer for A. Right? So this is a typical scenario of using reduction. So we have seen many such things. So we have seen specific problems which are reduced. So when we looked at linear programming, right, we saw that you could take a specific problem involving sort of carpet sales or involving making boxes of sweets and model it directly as linear programming. So that's not a reduction in a sense, because those are concrete problems which I am modeling as reduction. Whereas here we have actually taken one problem in one domain. I can take bipartite matching over arbitrary bipartite graphs. And any such problem, so there's a whole class of problems called bipartite matching. And I can take this entire class of problems and solve it using a class of problems called network flow. So that's really the reduction thing. I can take any bipartite matching problem and convert it to a specific network flow problem and reconstruct the answer. So that is the reduction power. It's not saying that you model one question in terms of some formalism, but you're saying that every problem of type A can be transformed into a problem of type B and the answer can be reconstructed. So when we say efficient, what we will usually mean, as we will go ahead, is that both these translations should be in polynomial time with respect to the size of the input of A. Okay. And the size of the output of B must also not be too large, because I have to reconstruct back in polynomial time an answer for A. So in this sense, bipartite matching reduces to maximum flow. Last time we saw that maximum flow actually reduces to linear programming, because we said that you can attach for each flow a variable. Then we can write these constraints which express the fact that the flows respect the capacities of the edges, and at each node there is a conservation of flow. The incoming flow must add up to the outgoing flow. So these are the constraints, these are two sets of constraints. One is the capacity constraints, one is this conservation constraint, and then we have this objective function which has maximized the flow through the edges coming out of the source node. Right? So maximum flow reduces to linear programming. Bipartite matching reduces to maximum flow, as we have just seen, and there could be other problems which we are not going to address here, but we will see a few examples later on. So the important thing is that these must be efficient. So what you can see is that when you do maximum flow to linear programming by adding one variable per edge, then the number of variables is now linear in the size of the graph, and the number of constraints is also linear, because we have one capacity constraint per edge and we have one conservation constraint per node. Right? So the problem in this pre-processing which converts should not create too large a solution. So that's the real goal of making a reduction effective in terms of translating efficient solutions. So this is the positive use of reductions in some sense. So we can take a problem that we know how to solve and use it to solve another problem. Now there is also another way of interpreting reductions. Supposing I do not know how to solve A, right? Supposing I do not know how to solve A, right? So I know that solving A is hard. Now I want to check whether solving B is also hard. So supposing I can reduce A to B in the same way, then I claim that B must also be hard, because if I could solve B easily, then I have a simple way of solving A easily. But since I believe that A is hard to solve, it cannot be easy to solve B. So this is a kind of an argument which would be difficult to do on your own. How do you look at a problem and say that this problem is going to, all instances of this problem are hard to solve? So on a specific problem, it's difficult to do this. But if I know some other problem where somebody has already done this hard work and established that that problem is difficult to solve, if I can reduce that problem to my problem, then I can argue that my problem must be as difficult as that one, because if I could solve this one easily, then through this reduction I can transfer it back. Right? So this says basically that if I can solve B efficiently, I can solve A efficiently. So conversely, if I cannot solve A efficiently, I cannot solve B efficiently. So the reason that we looked at linear programming and network flows is not to examine the algorithms for these. We just gave a sketchy version of the simplex version for how simplex works for linear programming, and we kind of illustrated how the Ford-Fulkerson algorithm works for network flows without actually proving that they are correct. But the point is that these are big hammers. So these are very powerful techniques which are available to us to solve a lot of problems. So many problems can be reduced to these, and these have in turn, because they are such useful problems, there are commercially available or even non-commercially available but publicly available libraries to solve these. So if you are using Python or if you are using some other programming language, you will find a way to call a library which can solve a linear programming problem for you. And if you can model your problem in terms of linear programming, then all you have to do is call this library. So therefore, it's useful to be able to do this translation. So this is a different aspect from the rest of the course, where we were looking at designing and analyzing specific algorithms for specific problems. Here we are saying that these are these very powerful problems which can be solved and for which solutions exist. So can you take your problem and interpret it as a linear programming problem, or can you take your problem and interpret it as a network flow problem and then apply the technique that generically applies to linear programming and network flow in order to solve it?